Turn it on someone?
No. Yeah. Okay, I think we'll go ahead and get started.
Okay. So the second part of the morning talks is a continuation of the manufacturing techniques for microfluidics. And in the morning, we've covered different direct microstructuring techniques, both mask-based and maskless. This part of the talk is about microstructuring via replication, where we're using some kind of tool that we typically call mold master. We replicate it either by hot embossing, injection molding, or casting. These are the major techniques used in microfabrication to form the part. The overall process flow for the replication techniques is you have to fabricate some kind of molding master via direct techniques that we just covered in the earlier today. Then we use those masters to mold, demold, to get our replicate. And in whole production scheme, we're only repeating this molding, demolding steps. So we can use single master for multiple, up to even millions of parts per master produced of the final device. So just to summarize difference between these two techniques from practical, let's say, production scale point of view, direct microstructuring, substrate, we process it, we got device, because every device needs the same type of processing. It's slow and expensive in general. Versus replication, we use substrate, just run the replication step, and we get device, which is in general fast and low cost. And one of the main technique used of replication used in making microfluidic devices is what's called PDMS casting, and I'm sure some of you are familiar with that. This is probably the most widespread technique in academia of making devices. I would say 95 to 98% of all articles on microfluidics were done over the years were done in PDMS. And so general material overview, it is PDMS devices these are rubbery material with hydrophobic surface. It's chemically resistant in aqueous environment, optically transparent, non-toxic, gas permeable, and it's also an insulator. By the way, PDMS stands for polydimethyl siloxane. Application in beyond the microfluidics, applications in industry as lubricants, adhesive sealants, and such a product that everybody knows like Rain X, Silly Putty, kinetic sand, or mounting solar panels. Food, in food industry as anti-foaming agent in cooking oil, beauty products, and medical devices. So these are the general proper applications of this engineering material. So what made it especially useful for microfabrication is that you can get really high replication fidelity down to nanometer range. The material is biocompatible, so you can do culture cells in the material, the organs on chip. It's transparent with low fluorescent background, which lets you do high resolution microscopy, chips for optical detection, for sensing applications. It's elastomeric, which is probably one of the most important feature that made it so widespread use, because it lets you fabricate on-chip valve and pumps. It also makes it very easy to make fluidic chip interconnects. In this chip, for example, you basically punch the hole in the material and stick the tube in it, and it sticks. It's gas permeable, which allows for on-chip self-culturing, organs on chip. You can also fill dead-end channels, which, for example, in hard plastic, like thermoplastics, it's not really possible. It's a two-part system. When we mix cross-linking agent with siloxane base, which lets you to tune material properties mostly with respect to its Young's modulus. And it's you can blend it with other fillers, for example, magnetic particles. It's easy to bond to itself in glass after you use the oxygen plasma pretreatment. It has really low cost replication setup. So you've seen in the morning, you've seen many pieces of equipment on the slide, many pieces of equipment that cost from hundreds of thousands to millions of dollars, right? Just to make lithography. The cost of replication setup, the basic one, you definitely can do below $5,000, right? It's also perfect for prototyping of proof of concept studies. That's why it made it so popular, especially in academia. Some limitations of this material: it's hydrophobic, it has low surface energy, so it typically requires surface modification prior use to improve wettability, reduce biomolecular adsorption. It is virtually impossible to deposit metals on the surface, so chips that, for example, require to have microelectrodes on them, typically it's done in a way that you deposit metal on the glass substrate and bond PDMS microfluidic part to the glass. It has relatively unstable surface chemistry, and Matt Jackson will cover it tomorrow in his talk. We'll talk more about this. It also absorbs organic molecules, mostly solvents and dyes, that can then leach out later from the material. May also release some of the organic molecules due to incomplete cross-linking, which may pose some biocompatibility issues. It is permeable to water vapor, so in the previous slide I gave you this as an advantage, but it also can be disadvantage if you try to control the evaporation from the chip. It's not that simple. It is really engineering material with main application for many other industries, right? So the properties that this material or application this material was developed for were a little bit different than microfluidics. So some of the composition variability of bulk material may not be an issue for regular industrial application, but very often is an issue for microfluidics. And for example, there's the biggest company that uses that commercialized PDMS devices is Fluidigm. And the material that's read somewhere that the material that they're using, they have to pre-screen every large batch of material. And about 90% of batches that they test, they do not accept, right? So there is some variability because it's mass-produced material. And it is at the same time, even that it's so inexpensive to use in the laboratory because student labor is cheap, right? When you try to mass produce it, it is way more expensive than other replication techniques. Okay, so let's just look how we make PDMS devices through casting. So as I mentioned, for any replication method, you have to fabricate the master first. Then you pre-treat the master, prepare your PDMS resin, remove the bubbles, pour over the master, bake, demold, and bond to the device. And it's schematically shown on the diagram here. Let's just go step by step. Practically, most of the SU8 of the masters for PDMS casting are photolithography pattern SU8 photoresist on silicon wafer, for example here. But we can also make the masters from different materials and techniques. And here's the example I mentioned in my earlier talk about the master that's made with the PMMA. And the advantage of this one was that in addition to the microfluidic part, it also had the macrofluidic port. So after casting, you didn't have to punch out all those 32 holes. After we have a master of, and nice thing about it, that the production of the master is probably the most expensive, but you can, for example, have it done by external company or your colleague at different institution. And then once you have the master, everything can be done literally on the 4 square feet in your corner of the lab, right? We pre-treat the master to improve the molding and prolong life of the master. And there are many different agents. And as you can see, the list of them is coming because people come up with different ideas how to modify masters to improve the molding. And it can be the methods to apply those different pretreatment agents, include vacuum deposition, solution phase deposition, evaporation. And the simplest setup pretty much is to have a desiccator, put your master inside the desiccator, put few drops of one of the pretreatment agents, evacuate the desiccator and leave it for a couple hours. And basically the vapors will redeposit on master and it gives you a nice thin coating that improves demolding. Mixing. So typically you mix base and cross-linker with the 10:1 by weight ratio. It's most common. However, you can adjust this ratio and that will change the Young's modulus. So you can make it either harder type of elastomer or softer. And that's especially useful when you're making microvalves and multi-layer structures. It's a good point too. So there are 2 most commonly used brands of PDMS. One is Silgard 184 from Dow Corning. And this is used typically for single layer devices. It has higher purity than the other brands. It is most common used material. Takes well to culturing mammalian cells. The other one is RTV 615, which is more robust. It's used for multi-layer chips and valve fabrication. However, it typically has lower purity than Silgard. So you take your 2 base and the hardener, you mix them 10:1 ratio. You do really, really good mixing, and what happens is during mixing, you introduce a lot of air bubbles from your mixing process. In order to avoid issues or defects in your device from entrapped air bubbles, we're doing degassing, which means you're taking the whole cup of the PDMS that you can see bubbles in it, put it in the desiccator, connect it, or any vacuum chamber connected to the vacuum pump, evacuate for 30 minutes to 2 hours, and slowly, under the reduced pressure, the bubbles will come out to the surface and your PDMS will be completely bubble-free. Tip for this one, it's really good to do this process. Don't do it in glass beakers, do it in the disposable containers. The other thing is if you use a little bit bigger, because if you apply a really high vacuum and you introduce all those bubbles, it will foam to the point that whole material can come out of the container. So just scale your container to the amount of PDMS you're using, basically. Pouring, the most important part of pouring PDMS is to put it really close to the surface and pour it in continuous way, not to introduce bubbles. Because if you do, you will have to take the whole Petri dish with your master into the desiccator or into the vacuum chamber and remove the bubbles again, right? Some of the application, like microvalves, may need thin layer of PDMS. So you can produce those by spin coating on the wafer. You can also, if you want to control really thin layer PDMS, you can also spin coat over your master. This will produce uniform, very thin PDMS devices. Typically, most of the devices that we use in the lab are, I would say, between 2 to 5 millimeters thick, because thickness of the material gives you a nice body of this rubbery material to insert your tubing to for pumping and pumping your reagents. So it's just purely from practical point of view. After the PDMS is poured over the master, we have to bake it, and you can actually leave the whole setup for a couple of days on the bench and it will cure. The moment you mix it, the reaction starts, but of course, higher temperature will speed up the process. The lifetime for the just premixed PDMS, it's about 1.5 hours that you have really nice low viscosity and can easily pour it, get good replication. And you can see higher temperature, you can really speed up the baking process and cure your device to achieve the final rubbery material. What you have to do in next step is basically use the razor blade, X-Acto knife, some way of cutting out the master with the PDMS out of your Petri dish, then lift it on the edge and very gently pull the whole layer off. In order to make the inlet-outlet holes, biopsy punches are probably work the best because you can get them in different diameters and they give really, really clean hole in your device. One of the features that it's really appreciated in bonding is in making PDMS devices is that you can bond PDMS to itself and to glass substrate simply by exposing it to oxygen plasma and plasma generator. What happens there, metals, what's this group name? SiCH3 groups are converted to silanol groups, and those groups are really reactive in the presence of other silanol groups. So if you put two parts that were activated, they basically bond instantaneously. So the whole bonding process can be done literally in 3 minutes, where 1 to 2 minutes is exposure to plasma and another to put it in conformal contact and press together. Typically, if you see poor bonding, it's because something wasn't clean, either your PDMS or your glass slide had some debris on it, had residual film that prevented it from good bonding. This is very advantageous if you do, let's say, single layer devices. Of course, when you do multiple layer devices, the idea that you put two things together and they instantly bond may be problematic because it makes it challenging to align different layers. And one of the solutions for this is, and you can see it in the clean room, is that this is home-built system by Ryan Grigsby. It's the PDMS aligner that uses microscope to cameras to look at the alignment mark, hold the two PDMS layers apart from each other. You align them and then you stick them together. Another nice tip that I got from him is that you actually can also modify PDMS devices internally with this Corona discharge device. Basically, you after your PDMS is already assembled, you can modify the inserts, so make it hydrophilic from hydrophobic simply by running this Corona wand above the chip. And so as far as the examples of PDMS, if anybody had an idea in microfluidic fields, you can be 100% sure that somebody either tried to make it or successfully made it in PDMS. pretty much from the beginning of microfluidics, from simple electrophoretic separation on chip through highly integrated chips. There are examples that it was done in microfluidics. I just pulled, so you can find a lot of literature on this subject. I just pulled two examples that use those pneumatic valves, also called quake valves, after the inventor of the valve. So this is multi-layer PDMS structure where you have a microfluidic channel, and then you have a valving pneumatic channel above it, and those channels are separated with very thin membrane in between. So if you increase pressure in this pneumatic channel, it will deform the membrane and close your fluidic channel, basically giving you valving operation. And this is one of the earlier applications when 400 PCR reactions were done in this multi-layer integrated system with a lot of valves, basically. So this application, and you can say molecular diagnostics. And the other one I like is this application that in plant biology, it's called root chip, where actually you put seedlings into those level reservoirs on the chip, and by pumping different reagents, you can observe how those plants, how roots of the plants respond to different environment on the chip. So material is very versatile in making chips, pretty much covers all different ranges of microfluidics making. And that's basically it. If you have any, do you have any questions? Okay.
What kind of pressures can apply to this material? PSI.
So that's a good question. It's probably just even below PSI or a couple PSIs. Material itself probably you have like silicone, which is PDMS tubing in medical applications. You can apply a couple of PSIs, but here it will all depend, and those valves would all depend on the thickness of the membrane and what channels do you want to close. But it's definitely not high pressure materials.